And we're live. Super excited to be back. It's only been 30 minutes since I was giving another workshop. I hope some of you were part of it. We teamed up with the great folks at Seed Studio for a workshop about how to use the Wii terminal, which is kind of an Arduino kind of device, and do some graphical programming, including some integration with IoT scenarios. In this workshop, and I hope you will share all the questions you have. In this workshop, we're going to build an artificial nose. Well, we're not going to build it from scratch, but some of you, especially if you're in the close or not so close TinyML/Edge Impulse galaxy and ecosystem, I'm sure you've heard the story of this silly, to some extent, device that happens to be an artificial nose powered by super low-cost gas sensors and microcontrollers. So I will briefly remind you what this device is, how it works, why it's important to some extent to keep in mind scenarios beyond just computer vision and vibration detection for TinyML. Like it's always nice to think about the kind of sensors that you have access to when you build your TinyML solutions. But whatever it is you do with TinyML, you're very likely turning sensor data or inputs, could be audio, turning those inputs into pretty much signals, right? And those signals, well, you can use them locally, and that's the beauty of TinyML. You can run with very little processing power, with very little energy as well. You can run an AI model, get some kind of signal, and then act upon it locally. Like usually TinyML, you think about it as pretty much an offline kind of scenario. And that's great because you're battery powered, you're off the grid, of the network. But what I want to share today is, especially for or in particular for a device like an artificial nose, why does it make sense to also think about connecting it, right? It's not only about building a device like you see here that can smell, right? It's so it's the Wii terminal that you're looking at, the main the brains, I guess, of the nose. It has an LCD display. It runs Edge Impulse, and within the enclosure of the nose, you would find gas sensors for picking up the smell of volatile organic compounds and carbon monoxide and whatnot. And the sensors like give some inputs to the Edge Impulse / TinyML model, and those inputs are processed, turned into and run through a classification model essentially, right? And so you get that, and you get some visual feedback in the form of two things actually, and I think it's worth mentioning. The actual result of the running the inference model. So in that case, being 99% confident that we've just smelled whiskey, and we also have the nice emoji there. There's also the emoji face on the right hand side, which right here is smiling. Earlier it was not so smiling; it was more like a wandering emoji face. Why is that? Like it's part of the TinyML algorithm in this particular artificial nose to not only try and smell, but also have the do some how would I call that? Some due diligence on the input data. If the input data doesn't really smell like anything the model has been trained on, then it actually triggers an anomaly. So the nose is capable of telling you that yes, the math says that the input kind of looks like it could be whiskey, but since it's not really something the model has been technically trained on, then you have this flagged on the screen, right? So that's the device, but it's although you can maybe pick up the wireless icon on the LCD display. Initially, when I created this device, it wasn't in any form or shape an IoT or a connected device. So let's talk about it in more details. Briefly, a few words about myself. I'm French. I'm going like all in on the French cliche with the baguette and so on. But I do happen to work for Microsoft as part of the Azure IoT product team, and I'm one of the interfaces with the open source communities out there, the developer communities around all things TinyML, open source, open hardware, LPWA, kind of low power wireless protocols, trying to make sure that whoever is familiar with those third-party communities and loves, and for good reasons, the tools and the ecosystem that they can find in such or such tech community out there, we make sure that we have the right bridges and the right relationships with those communities, so that they have a great experience when it comes when time comes to connect their solutions to the Internet of Things. Because one way or the other, many solutions out there and end up one way or the other participating in IoT scenarios, and that's very true for TinyML. So a few words and some quick background on the artificial nose. Like I just mentioned, I'm French, and I'm a software engineer. I've been a software engineer for almost 2 decades now. I'm pretty comfortable with like several programming languages and frameworks and embedded development and front-end development. Like, I can get my head around a fair amount of concepts, but for some reason, AI is something that eluded me, and that was too abstract for me, I guess. So early in the pandemic, back in May of last year, I had this idea of using wireless, of using open hardware, open hardware sensors for building a device that would hopefully leverage ML and AI to tell me how to improve my bread recipe, and to smell essentially and detect when my sourdough starter would be perfectly fermented. So I had this sort of intuition that I could use AI to correlate whatever the gas sensors would tell me in terms of concentration of carbon monoxide and ethyl alcohol and whatnot in the air, and the quality of the bread that eventually, after actually baking the bread, I would get, right? So that was the idea. It turns out that in just a few hours, not only was I able to finally understand what neural networks really were and things like that, but the project also got super popular, and it ended up being featured in several magazines and on websites like Mashable.com. And that was really great to see, and that's not like strictly speaking the point of today's conversation and presentation, but that was great to see in that it made me realize that there's we as people evolving and being neck deep into tech, we assume that AI, ML, like the basics of AI and ML are pretty much understood by now, and people realize what the applications could be, etc. But when this project got viral, I actually realized that many people, and probably some of you, and maybe some of you attending today, people didn't necessarily know that gas sensors existed, let alone they could be used in combination with neural networks to do artificial smell kind of scenarios. So that was for the pure let's build an artificial nose kind of aspect. Then I realized that an artificial nose only takes you so far if you don't connect it to the internet. And what do I mean by that? Let's look a bit into the hardware for the artificial nose first. So it's using the Wio terminal. It's kind of an Arduino on steroids. It's effectively the MCU is a cortex-m4. And I have another slide about that, but it's reasonably constrained device, right? Which I paired with a gas sensor. I think it costs something like $30 US. With $30 US, you effectively have an electronic sensor that can tell you the concentration of carbon monoxide, ethyl alcohol, and a few other compounds in the air. So that's That's the heart of the hardware. And then diving a bit closer and deeper into the Wii or terminal, you have this cortex-m4F, like I mentioned. So it's constrained and maybe not so constrained, depending on how you look at it. I don't know if half a megabyte of flash and 200 kilobytes of RAM is something that you would call constrained. It's there are certainly devices that are more constrained than that, which I could have used because I actually realized that I don't necessarily require all the processing power of the Wii or terminal, quite interestingly, and I could do with a device that would be 10 times less powerful easily. So that's something, fun fact, I guess. And something that's interesting with the Wii or terminal, it's paired with it has a Wi-Fi chip, Wi-Fi and Bluetooth chip, which means that once I was done, and that's not the main focus of today's workshop, once I was done with training my model, which essentially consists in just smelling a few things for a few seconds and like labeling those things and those gas concentrations, associating them to some smells. Because another fun fact is that my sourdough starter kind of experiment, I actually realized it would probably be too difficult to do that and bake dozens and dozens of loaves of bread to train my model. So effectively, I trained the model against all sorts of smelly things, coffee, whiskey, etc. And so that's what I did. Training the anomaly detection algorithm as well. And then I had this, except for the wireless connection thingy, but I had this device that's great. Like literally in like half a second, it can pick up a new smell and give you a visual feedback locally. Granted that you look at the device, it gives you some information. That's great. But then what happens when you want to take the device to the next level and use it for real scenarios, or at least for more than just having a toy, a fun toy that can smell whiskey and coffee? What if you start thinking of actual industrial scenarios? Things like, I'm in the business of facility management, and my service is I offer a service where I go and clean public restrooms and restrooms in office buildings and so on. And so I could very well imagine improving the way I manage my business, where rather than sending cleaning personnel every day, like literally every day at 5 a.m. or at 10 p.m. at night, someone goes there and does some cleaning, no matter what. What if I could actually do it in a much smarter way by only sending people to clean the room when it's actually needed, right? And when a sniffing device tells me, hey, you know what, it doesn't smell so great in there, you may want to send someone. And that could be nice, especially in those times where due to COVID, office spaces might not be as busy as they once were. So it might make sense to optimize for so many reasons, right? It makes sense to optimize the way you run the cleaning schedules. So you could think about deploying the sniffing device somewhere in the room, right? And so it's very likely that the device is going to be somewhere in the ceiling, right? Because if it's anywhere else, it's you don't want to send someone go and read the screen that you saw earlier on this particular picture. It doesn't make sense to go and see on the screen, oh yeah, the device says that it stinks in there. No, it needs to be something that's literally working remotely, and you want to use and leverage TinyML to have a device as tiny, as cost-effective, as cheap as possible, deployed in there in your thousands of buildings and restrooms out there. And that device turns sensor data, physical data, into meaningful signals the air is clean, the air stinks kind of signal. And then that particular signal you send potentially to the internet, or at least you send and you route somehow to your information systems so that you can act upon the signal. And that's where you start combining what I would call intelligence at the edge, and like the essence of TinyML with the internet. And that's IoT is also a term you may have heard, right? And so think about like this super simplified vision, but which is effectively what we're trying to accomplish today in the workshop, where you have a TinyML device, or a device that's reasonably smart and intelligent, that lives at the edge. And then you have your cloud, you have your information systems. If I'm going back to the facility management company I was referring to earlier, it's likely that those guys have been in the business of cleaning and selling their services for decades, right? So it's not like they already have an information system. They would like to somehow feed and augment their information system with the kind of information and signals that they get from their smart/TinyML devices. Things like telemetry, right? The signals in the form of raw sensor data, potentially, that it might make sense if we're switching gears and looking more at maybe the chemical industry. For them, it's not about the air stinking or not stinking. It's about the air being saturated in ammoniac kind of stuff. So sensor data, accessing sensor data over the air might make a lot of sense. And or getting like the actual signal of the TinyML algorithm telling them it smells with a 95% level of confidence. It smells bad in that particular room. Here's your signal. And it goes both ways, right? It can also be from the cloud. You want to control the devices and do things like potentially update the TinyML models over the air. That's also a very useful scenario, right? So what I want to show you is how to accomplish just that by using, so whatever I'm going to say is very replicable and very, you can mirror whatever I'm going to say with any other IoT platform out there. So my point is not to sell you the Microsoft Azure IoT cloud, but it's more about selling you the value of adding IoT to your TinyML use cases. So we're going to look at connecting to Azure IoT Central. And in a nutshell, it's going to be four steps. First, when you when you build a device from scratch, you're going to identify what is the manifest, the contract, the model, you call it however you'd like, of your device in terms of what is the kind of information I would like to make accessible over the air. For the nose, I'm probably going to think about, I wouldn't mind getting the sensor data sent to the cloud, because it might be useful to archive my decades and decades of sensor data. Like, it's useful information for doing data mining later on and things like that. Or maybe it's not, but I mean, you think about the device's contract, right? And then once you have done that, once you've agreed with all your stakeholders on what is the data that you really want to route eventually to your information systems, then all that is left, and it's literally just like a few lines of code, and we'll look at how those lines of code look like. You sort of bind whatever you've modeled in the contract to whatever it is in your embedded software that is producing or requiring this data, right? My Edge Impulse model, my TensorFlow Lite model is giving me, I do some computer vision algorithm, and it's giving me the class of whatever object it has detected. Well, this particular variable in my code is something that I'm going to bind to a primitive in the Azure IoT SDK, in my IoT SDK, so that it's effectively reflected in the cloud, right? And so step 1 and 2, just like so that it's clear, is something that I, as the nose designer, hardware designer / inventor, I went through, but when you build an IoT solution, you might end up reusing existing IoT hardware, existing IoT sensors. So there is a very good chance that if you use as part of your IoT solution off-the-shelf devices as opposed to devices that you're building yourself, then it's very likely that they are already supported as IoT plug-and-play devices. And hence, someone has done the job for you already. And the only thing you care about is them letting you know, here's the contract of how you may interact with my device from the cloud. So, but yeah, that's for the modeling. And then once we've done that, I mean, the only thing we need to do is to effectively connect the device to our own IoT platform, right? It's not like all the billions of devices that participate in Internet of Things scenarios. They all live happily on the same World Wide Web, right? Everyone wants to ensure privacy and to ensure that their solution live in their own environment. So we're going to see what that actually means to deploy and to have your own more or less private IoT environment where you effectively decide what are the credentials that your device may use to connect, and what are the credentials that you may need to have your IoT data effectively be routed to third-party systems, be it an SAP backend, an SAP ERP kind of system, or anything really, right? And once we've done that, then we effectively have IoT data, IoT signals available in the cloud. And then that's step 4. And then that's a lot of fun. And we'll see about that. But a few more words about the contract thingy. Why that is really important actually to think about it. When you build a TinyML solution or any embedded solution, really, connecting it to the internet is not that hard. It's granted that you have a Wi-Fi module/modem and or a cellular modem, or if you do LoRaWAN, Sigfox, sending bits and bytes to the internet and to a third-party server. It's not that hard. And so it's not that hard to have the hello nose, say and share and push to a remote server whatever data, whatever variables it is producing. Hey, 73. I just picked up 73. Dear IoT server and or dear endpoint, there you go. Like, here's my data. Okay. Do you mean 73 as in 73% of humidity? Do you mean 73 as in 73 degrees Fahrenheit in terms of like temperature and heat? Is this 73 ppms, part per million of ethyl alcohol? It's not clear, right? I mean, you need more than just the data. You need metadata to characterize what it is that your device is sending to the cloud, and or how is it that you're going to send information to the device to act on it, right? To reconfigure it, to change its behavior. So you need some kind of standards to do that, right? To make sure that you have interoperability at the end of the day, because otherwise, yes, you have signals that may be in your own silo. Like if you're building both the device and the server and the mobile applications and the web applications and whatever are going to be the consumers of the data, maybe you know that 73 is what it is supposed to be. I don't know, maybe it's humidity. But if you start like looking at interoperability and how eventually your partners and your customers and your vendors are going to extend on your solution, they need more than just like a Word document somewhere that says, oh yeah, 73, like whenever the device is sending a number, that number is the humidity level, and sometimes it also sends a string, and the string is something else, and that's our contract. Remember to look at the Word document, right? That's not how it works. You want to think about it in a way more formal way. And in general, and again, this is applicable to more than just Azure IoT, it's been like a while now since the IoT industry at large has sort of agreed on the fact that, in a nutshell, you have things like telemetry, properties, and commands. Telemetry is something more in the form of the data that a device might produce. For the nose, this would be things like sensor readings, right? Maybe every 5 seconds, I want to send to the cloud the raw sensor data, like volatile organic compound concentrations in ppm, and specifically mentions that somewhere in the contract that that the unit is ppms, and same for ethyl alcohol concentration, and et cetera. Then maybe you have things like properties, like you want to report at regular interval what is the current smell, right? And it's something that's always there. It's a property of the nose, right? That it once in a while the property changes, but it's always there. Similarly, the reporting interval might be something that you want to know and change potentially. And then you have commands. I didn't implement any commands just yet on the device, but I'll come back to that later. But typically a command could be updating, like pushing a new TensorFlow Lite / AI model to the device. So that would be an option. And so the way it works in the Azure IoT ecosystem, it's using what we call the digital twin definition language. So essentially that contract that I said and sort of discouraged you to maintain in some kind of Word document as part of the, yeah, sure, we know how the device is supposed to send data. No, DTDL is something that really allows you to do it in a standard way. It's kind of a meta model, if you will, or grammar, a schema for describing the contract, right? And it's at the end of the day, it's baked into the device. So you have like you're constrained in the way you talk to the device, but for good reasons, because you now know for sure what is the data that you're going to manipulate. And so when I created the nose, I had to author my own DTDL model. So it's something that I could have done in the cloud, like straight from the Azure IoT Central cloud portal that we will see in a bit, or this is something that you could author almost as you would author some code. It is a document, a JSON document, more or less, that you can author. And once you're happy with it, you can actually make it public, so that if you end up sharing your device or sharing whatever is the data your device is producing with the rest of the world, then the rest of the world, they have access to the contract. So they know way more about the device and about its data than if they were on their own having to read the spec and to read the doc. No, it's sort of, it comes with the device, right? And it's part of the so-called Azure IoT device model repository, where you have, by now, I think we have like, literally hundreds of devices that are there and that are listed there. And the document, how does it look like in a nutshell? And it's literally how the model is made, right? So my point is not to drown you through thousands of lines of code in today's workshop, but the code I'm actually showing you is the code from the artificial nose project. So here, in just a nutshell, but we're looking at an artificial nose model that has a unique identifier, some metadata to describe like what is the artificial nose exactly, and then the artificial nose has some elements to it, right? It could be, again, properties, telemetry, or commands. The properties are things like, what is the last thing that the device has smelled? That's a string. That's a string that's going to say something like coffee 99%. That's the property. There's another property. This one is writable. This can be changed from the cloud. It's meant to be, it describes how often the device will be reporting its status to the cloud. So that's the telemetry interval. It's something that you can change. And then there is something else, which is, interesting. It's a component, and it looks like it's a third-party component. So that one is actually interesting. When I built the nose, I built the nose, but I didn't build the gas sensor. The gas sensor already existed. It's from Seed Studio. I could have used maybe a sensor from Bosch or from Microchip or whoever else does MEMS gas sensors. And rather than redescribing my own interface for it, it might already exist, and I can capitalize on this ecosystem of metadata so that I get even more interoperability. So the particular gas sensor, if we look at it, it's a model that's similar to the nose model, except that this one is really tailored and geared towards just the gas sensor. And it has all the telemetry entries for volatile organic compounds, for carbon monoxide, etc., etc. And it has, it has all that. And it's a public model that everyone can piggyback to some extent. That's for describing the contract, literally just like, putting together. And I mean, the tricky bit here is not about writing the model. It's more about thinking, what is the data that I want to expose to the rest of the world? What is it that is really going to shine and be useful when I start routing it to the cloud? Because I want to leverage TinyML for what it's good at, having intelligence that doesn't require the cloud to happen. But then I also need the cloud to have access to more context, right? And to have access to more, a more dynamic kind of behavior. It's one thing to know that it smells bad somewhere, but it's something else entirely to know that it smells bad in a particular facility for which on a particular day, it's a particular person who is responsible for cleaning and for servicing the building, but that particular person entered in the system that they are on sick leave. So we should look at pinging someone else, right? It's not like you want to have this kind of logic on the device. You want to offload some of that to the cloud. But long story short, once I have the contract, and I want to remind, and I know Alessandro has done a great job at that already, but I don't see any questions so far. Maybe that's a good news, or maybe not. Please ask any random question you may have. And now is your chance. It's more or less the first time I'm giving this particular presentation. So questions and feedback also is most welcome. So I have the contract of my artificial nose. Next come the time where it's time to effectively connect it to the internet, right? And to sort of, it's not like I'm connecting random embedded code to IoT. It's embedded code that comes out of the Edge Impulse SDK. So what I need essentially is to combine the best of both worlds. And what does that mean exactly? On one hand, I'm going to use the Edge Impulse SDK for sure for running the inference and so on. But then I also need potentially and probably another SDK when it comes to integrating with Azure and more specifically with Azure IoT. So for that, I'm going to rely on the Azure SDK for Embedded C, which, by the way, allows you to connect your embedded devices to much more than just Azure IoT, right? There are other Azure cloud services that you may want to integrate in your Azure small, tiny devices. But for IoT specifically, the SDK provides primitives for helping you craft more or less craft the network packets that you need to have in order to communicate with the Azure IoT platform. And then the only thing that you need to bring on top of that is your own, something that, and that's kind of true as well for the TensorFlow Lite ecosystem and for embedded in general. Embedded SDKs, there's often a generic aspect to them. And then there's the part where it's time to effectively do the porting to dedicated silicon or do the porting to dedicated tool chains and BSPs and whatnot. And so essentially the Azure IoT SDK for Embedded C provides you with the primitives, but it's not like it's providing you with the the TCP/IP stack for effectively connecting to the internet, or the TLS stack for doing so in a secured fashion. So you need to add that and to bring that to the mix, which the community is doing, right? Like the ESP32 is doing that in their own way, and then STMicro may have some dedicated higher level kind of SDKs for Azure IoT, and for the WIO terminal specifically, there is a library that does just that, right? And that leverages whatever TCP/IP, TLS, MQTT as well. I'm not sure if you've heard about the MQTT protocol, but it's kind of the de facto standard for IoT. All those libraries are already available as part of the WIO terminal ecosystem. And Seed has done the work of providing you with a library that is effectively the Azure IoT SDK, tailored towards the WIO terminal ecosystem and way of approaching things and APIs. And so in practice, once I had my artificial nose, I was tinkering with the Edge Impulse APIs, right? I was like, okay, let's read data from my gas sensors. Let's put the data into some kind of internal buffer in memory, and then let's just run the data through the fancy Edge Impulse DSP blocks, so that from my raw sensor data, I would extract some meaningful features, and then let's run the data through the neural network, and then, oh, perfect, I have a result. I have a classification result that tells me that the class that the nose picked up is coffee or is whiskey, and the confidence is X%, right? So that's what the SDK, the Edge Impulse SDK would give me. And then I just need to connect the dots with the Azure IoT SDK, or rather with the library that Seed and the WIO terminal has on top of the Azure IoT SDK. And essentially, it's as simple as an API that's allowing you to send telemetry when it comes to telemetry. And sending telemetry, how does that work? A telemetry is a JSON payload, like a set of attributes for which like you want to send the value, and a so-called component name as per the contract, right? If I were to look at how I would potentially call the API if I want to send my raw gas sensor data, like concentration of NO2, CO, ethyl alcohol, and VOC, volatile organic compounds, it's literally like that's the code from the artificial nose project. It's building a JSON document where you have some keys and values for the NO2, and in front of that, you would have the number, like the actual float for the concentration of NO2, similarly for CO, et cetera, and then you send the telemetry to the cloud, but it's not like just a random JSON document, because you would be back to the problem earlier of not really having a contract, right? Is the NO2 and the CO, is it sent by sensor number 1 or sensor number 2, assuming that the nose maybe has 2 sensors, right? And so for that, you actually have this notion of the component name, right? And so it's not a random sensor that sent the data, it is the gas sensor of the nose, and there might be a secondary sensor, and in which case I would use a different component name if I were to send data on behalf this sensor. That's for telemetry. And for properties, it's very, very similar. It's what we'll call twin patches, in that a property is effectively something that lives both on the device itself and in the cloud. And you want to try and keep them in sync, right? If you have a property of the nose, like the general concept of the nose, it smells like at a given point in time, it is smelling something. And so the nose, like the embedded device itself, it has its own representation of that. And once in a while, it might want to make the cloud aware of that representation, right? And so you have two twins, right? The physical counterpart is the device and its embedded code, and you have the digital twin living in the cloud. And by means of the API that we're looking at here, send twin patch, you're effectively from the device telling the cloud, hey, here's an update that you may want to consider to my local state. You may want to mirror my local state on the cloud side of things. And again, super simple to do. That's code like literally copy pasted from. So I didn't share the link to the GitHub just yet, but if you were to browse the GitHub repo for the artificial nose, you would find literally those lines, except maybe for this guy here. I hard coded the value here. This is the value that you would get out of the Edge Impulse SDK, right? Out of the Edge Impulse SDK, I run my model and I get some information in terms of what class got picked up by my classification model and with which level of confidence. And this becomes the string. Like earlier when I modeled the contract for my device, I said that I wouldn't mind having a property that's called latest inference result, and that would be essentially meant to reflect what is the latest smell I picked up. And so by means of those few lines of code, I'm effectively locally on the device in my embedded code preparing a JSON document where I say, hey, the new value for coffee is, the new value for the inference result is coffee 99%. And then I turn that into an actual JSON document, which I send to the cloud, right? And with that, I'm letting the cloud aware of a change to a particular property. And so once I'm at that point, essentially, I have embedded code that is ready to communicate with the Azure IoT cloud. What it might be missing, though, is, I mean, it's the cloud, but which cloud specifically? I want to connect. Not only at some point I will need to connect to make sure that the Wio terminal device is authenticated against my a Wi-Fi hotspot and effectively gets access to the internet, but also I need to at some point provide the credentials to what is the particular internet endpoint where I want my telemetry to be sent to, right? It's not like it's anyone's. It's really my own solution. And so there, I'm essentially going to show you what happens. Sorry, when you want to like connect data to IoT Central, you effectively do that by going to, and this is something that you can, I have tons of instructions out there on how to connect the artificial nose to IoT Central. This is something that doesn't require you to have like an Azure paid subscription. Like you can try things out even with for free, right? So that's you go to azure-iotcentral.com and you can start building your own solution, right? That endpoint I was mentioning earlier, that's something that happens once you start your own IoT Central application. Essentially, you create your own IoT platform, your own instance of an IoT platform that's going to manage your devices, your data, your digital twins, which I started to hint at. But yeah, you can just go ahead and create a new app, right? And like I just said, again, this is something that can be entirely free. You can try things out. Either like you have this option here or this option here. I mean, you can really get started easily for free. And once you have created your application, I've already done that beforehand, so I won't go through that process here, but I have created an application for connecting, managing my noses, right? And so there's already a few devices that are connected, but I'm actually, and let me see. So you should be able to see so this is my artificial nose device. It's already connected. So I'm actually going to turn it off. I don't want any device to be connected to my platform just yet. So making sure I have no device. Let's see, it should be gone now. Yeah, it's gone. So I have no device. So this is virtually where you would start if you were to create your own IoT Central application. And then you want to connect devices. And how do you do that? What is the information you need to tell your artificial nose or whatever is your IoT plug and play device? What is the information you need to connect it? Well, it's something that you can easily find here. Like you have essentially a set of credentials that you will need to use in your devices to connect them to this particular Azure IoT Central platform, right? And so it comes in the form of a so-called ID scope plus another a set of keys that I won't show on screen here, but that's essentially what's and you could use certificates as well as in like X509 certificates, but I mean, it's what you need to connect to the device, just like you would need credentials to configure your Google Home or your Alexa at home. It's similar, right? You connect to the Wi-Fi first, and then you connect against some kind of a third-party service. That's exactly what needs to be done. This can be done like both setting up the Wi-Fi and the Azure IoT Central credentials. It's something that could be done in the factory, depending on like, your use case. You may be able to actually pre-program some of the settings there, and ideally also flash this in a secure piece of silicon so that the secrets cannot be extracted by malicious actors. The process might be manual. It's actually the case for the artificial nose. Configuring the Wi-Fi credentials and the Azure IoT Central credentials for the artificial nose is something that you would do over serial. So it's a fairly manual process, but it's just for the sake of the proof of concept. It could be, I could very well, and I will, or maybe you will beat me to it and do a pull request to the repo. I could implement some kind of scenario where it's more using maybe Bluetooth and a Bluetooth companion kind of app, and pairing the device and claiming ownership of the artificial nose could be something very, very similar to the way it works for devices like Google Home or Alexa. You can use TPMs and like the secure silicon to do some of the authentication as well. But I think you get the idea. But long story short, the device that we're looking at here on the screen or on my webcam. Right now, I turned it off, but I will power it up again. So it's going to tell me a few things. Let's see, making sure that I think you can see it reasonably well. So it's turning on right now. It's connecting to Wi-Fi. It's once the Wi-Fi is connected, it's getting time information as well to make sure that we get accurate time and date, and then it connects to Azure IoT Central. So if I switch back here to my Azure IoT Central platform, my nose is back, right? I deleted it earlier, but it just got re-provisioned all over again, and it starts sending data to the cloud. It starts reporting telemetry in real time. So that's my local time. Yes, it's Friday night, and it's beer o'clock, way past beer o'clock here. But it's the device is connected. It's sending data which I can display in real time on some graphs. So, long story short, I've effectively connected my device to an Azure IoT platform, and it's only the beginning, actually. So with the time I have left, I want to show you a few more things. So now I have a nose, a device that's, and you still see it here. So let me maybe just quickly, making sure that you see it reasonably well. Right now it's in training mode. So I'm going to switch the device to the so-called inference mode. And now it is, let's see, let's just make sure. Okay, I'm going to actually go slightly wider. Let's see. Yep. So there we go. What is this? This is a can of Italian coffee powder. So it turns out the nose has been trained to actually smell coffee. So right now the nose, and now since it's a bit small, just zoom just a bit. nose is telling me that what it is smelling is ambient air with a reasonably good amount of confidence. I'm going to take the gas sensor that you see here and put it in the can of coffee. And now the device is, when I told you earlier that it reacts really quickly, it does, right? It's now telling me that it's picking up coffee with 100% of accuracy. So that's great because, I mean, not only the device is working, but it is connected to the Azure IoT platform, which means that if I go back here real quick, so not only do we have like the raw telemetry that evolved, and again, that's the local time right here, 8:51, and then some seconds. But if I go here, we also have the latest inference result, right? So that's great. We have data flowing into the system. And that's, like I said, that's only the beginning. Only the beginning in that. So you don't need that. You saw that particular demo. In that, in a nutshell, we've built this. So I'm going to go back on camera, maybe. There we go. We've built this solution where we use a gas sensor and a model that we've trained using Edge Impulse to run some inference and effectively smell. And then once we've smelled something, as per the contract that we spent some time thinking about, we realized that it might be a good idea to take the inference result, aka the smell, and send it to Azure IoT Central. And once we've done that, there's actually quite a lot that can happen. It's not just about having a dashboard where I can look at just one nose and getting a sense of what the nose is currently smelling and picking up. It's also about having access to APIs to potentially take the data to other third-party systems, but also some rules to be like, if I'm picking up the smell of coffee for, well, let's just scratch that. If I'm picking up the smell of burning food for more than 5 seconds, send an alert, like trigger an alert, whatever an alert is for you, sending an SMS, logging a ticket in Jira, could be anything really, right? And or you could implement some kind of data exports. And so we're going to do just that, right? A quick demo of how it looks like, maybe how some of that looks like in IoT Central in terms of visualizing data, implementing some rules, right? So quickly switching back to Azure IoT Central, the things that I may want to implement would be maybe data visualization. I want to look at all my artificial noses out there, and I want to graph the gas concentration over time. And interestingly, over the past 15 minutes, it's interesting to look at it, right? Because over the past 15 minutes, we used to smell very little amounts of ethyl alcohol and CO, etc. But now that we have the sensor dug into the can of coffee, then we have a way higher concentration there, right? So that's one thing that we could be doing. Another thing would be implementing some rules. I want to create a rule where whenever something happens with my artificial nose devices, and I might have others, right? This is just listing me what are the different contracts, right? If I have other like smart thermostats and whatever else in my solution, they all have their own models, their own contracts. And so for each device that belongs to a particular class, a particular category, I want to implement a rule. If a particular condition is true for a period of time of 5 minutes, and that condition could be, I don't know, the CO level is greater than, the minimum amount of CO is greater than 20 ppms, plus maybe some other actions, then I want to send an email. I want to send an SMS. I want to trigger a Power Automate no-code kind of workflow you might be familiar with if this then that online service. Power Automate is very similar in a sense, right? You can really easily mash up and build your own business rules, which is really, really, really good. So that's my means of using IoT Central, and only IoT Central. I can already do a lot. And then you may want to do even more. So let's see what I mean by that. I think there was a couple questions, or at least one. Let's see. I want to make sure I don't wait too long. A question from Joshua. Is it possible to expand this by having multiple devices on a mesh network and have central device communicate with Azure IoT? Pros and cons. Really, really good question and good point. Yes, this kind of architecture would be something that you would be that's an architecture that involves a so-called gateway. Like usually you would call the kind of central device that communicates the gateway. And so the gateway is not as dumb as the TinyML potentially battery-powered sensors, but it's not as smart and as clever as the cloud. It's kind of in between, right? So it might be smart enough that it's capable of handling the potential complexity of rolling out firmware upgrade to the devices, right? Something that the devices might not be able to manage on their own because they don't have enough memory to do that. They don't have enough storage and whatnot. But maybe the edge gateway, Raspberry Pi kind of device, really, or maybe the more rugged version of it, is it's totally a very valid scenario. And the pros and cons usually relies. How should I say that? The key factors that you to take your decisions here would be: is it like how much do you care about security? How much do you care about having maybe your mesh local network manipulating some confidential data that is safe to expose at the gateway level, but some of that data you might not want to route on the public internet. So those kind of factors would be something you'd have in mind. Question from Vistali on the over-the-air updates. Actually, I have a slide about that. So that's actually a really good question, especially when you have really small devices where re-erasing and reflashing the device as it's running can be a tricky challenge. So that's really good question. We will answer it towards the end. So yeah, I want to wrap things up by telling you about doing more than just like at the end of the day, what we saw through IoT Central is looking at the data produced by the devices, but very much still in a pretty siloed kind of approach. We have dozens and dozens of noses potentially sending data to IoT Central. Then we have other sensors, other IoT devices sending data to the very same IoT Central environment. But then there's everything else. There's everything else that you have in your existing enterprise system. If we think about, again, the scenario of a company that does facility management, they've been in the business for literally decades. And so they know how to, have existing models and existing representations in digital representations of the buildings and how are the buildings composed of different floors, and the floors may have HVAC systems and things like that. And yes, someone is teasing the demo, so now I need to not mess up the demo. But yes, it's going to be a really cool demo. What's my point? My point is you have existing systems and you want to augment those systems with systems that have nothing to do with IoT whatsoever, that may have nothing to do with sensors whatsoever. But those existing systems, you want to augment them with additional entities that may have a physical counterpart, like Nose XYZ is a new entity that potentially now exists in the system, especially since now it's connected to Azure IoT. We can probably route the data towards in the system, so that whenever, again, what I referred to as a signal, whenever this particular device, this particular entity is sending a signal that says foul air, it's not just a signal that is very device centric and that might be difficult to put in context. No, the context might be there. Like, you may have this notion really of digital twins, where you model the entire knowledge graph of how your different entities, whether it's entries in your ERP system or entities that are IoT devices, legacy systems and whatnot, they all have relationship between one another. And then such or such entity send a signal, and that signal you can really put in context. Oh yeah, the nose, or right now, when whoever deployed the nose in the ceiling of Tribune Tower, it did so on floor 3 of Tribune Tower in Chicago. And so when the device was initially provisioned, this relationship was established. It might evolve over time. Maybe the device will be decommissioned or will be moved from one floor to the other. But what's important is that at a given point in time, the nose is somewhere. And so when the nose says it smells nasty, where is there? There is, I mean, you just need to navigate the graph, right? And so, yes, the nose is deployed on floor 3 of such and such building. And who is responsible for cleaning the building today? Oh, it's John. Let's send them an alert, right? And so you can really build way more complex, way more rich kind of scenarios. And so I want to show you a demo where we're going to do just that, not necessarily the context of facility management and cleaning buildings, but just want to sort of open the door to other scenarios where I think a device like the artificial nose can be relevant. Things like a retirement home, and you have elderly people that do their best to live in their apartments, and but it's tricky, right? Because there's tons of dangers, and it could be that they have like they burn their steak, and then the kitchen stove is on fire, and then there's like an actual danger there, and or you want to be able, like, as a relative, or as someone, as a nurse in the retirement home, you want to have access to information such as the mood, almost, like, right, and the mental health of the people living in the house, by means of, did they pour themselves coffee today? Like, usually this person is when they're in a bad mood, we know that they don't pour themselves coffee, and we want to have this kind of signal. And potentially, how about going all the way to the point where we want to have that feedback in a very, very interactive fashion, right? And have almost like a dashboard where we're not looking at graphs and at KPIs, but potentially at the virtual representation of the person's home, right? So that's what I want to show you real quick. How would I go about doing just that? And I dismissed my presentation by accident. Two things. One is I'm complementing Azure IoT Central with something that's called, sorry about the flickering, and just there we go. I am going to complement IoT Central with something that's called Azure Digital Twins. In a nutshell, this is what's allowing me to model the graph, the knowledge graph that we saw earlier. Literally, I mean, it's very, very similar to the graph you saw with Chicago, the city of Chicago, and the buildings and the floors in the buildings. It's kind of the same here. I'm modeling the different buildings in the retirement facility and retirement home, the different rooms, and then potentially those rooms will have some sniffing artificial nose devices attached to them, and maybe thermostats and whatnot. And so that's my digital twin. And this digital twin can be fed and can be populated with data coming from a wide variety of sources. It could be Azure IoT Central. It could be AWS IoT. I don't see anything wrong about that. It could be anything really, but then it becomes sort of the source of truth when it comes to what is my what's happening in my ecosystem or in my environment. And so one thing that I need to do in order to have more than just sort of static representations of building, kitchen, etc., is go quickly to my IoT Central environment. In the data export section of the user interface, I have already configured a webhook, an endpoint that corresponds to the Azure Digital Twin, ADT endpoint. And what I want to do is implement an overall rule, if you will, a generic, or I should say a root, actually. I want a root that's always active and that is taking data, like whenever a property changes for a device that is an artificial nose, I want to send the data to the so-called ADT webhook before I save that information. I'm actually going to, I can actually save it. So let's see. So the webhook is now active. It's starting. Let's just refresh until we're 100% sure that it is running. I'm going to switch back to my IP camera, going with the close-up there. So yeah, the root is active, it's healthy. So it's fair to assume that we are sending data to Azure Digital Twins. I'm going to actually make sure that we're spelling something else than coffee now. Yeah, coffee. And going back to Azure Digital Twins. Now we should have, it might take a bit until the sensor actually starts sort of desaturating and smells something else. And now it's back to smelling ambient air. So I can refresh my environment here. Come on, yeah, there we go. We have a new digital twin. That's interesting. That means that essentially the environment is now made up of a new thing. That thing is seems to be pretty orphan. It's not in the kitchen. It's not in the living room. So it would be part of the provisioning process of installing the nose in the person's home to, at some point, establish the relationship between and be like, okay, the nose, we did deploy it in the kitchen, right? But I'll wait just one more minute until I do just that. What I want to show you is this. This is Blender. The actual framework I used doesn't really matter much. I could have used maybe Unity or any other like CAD software. I just wanted to show you some kind of like different visualization than what you might be typically used to. But in Blender, what I did, Blender is an environment that allows me to do 3D modeling and 3D design. So I literally loaded the floor plan of the person's retirement apartment, right? And so it's here. It looks nice. You can zoom and blah, blah, blah. But Blender, just like virtually any other CAD software out there, can be scripted, right? And so I've effectively, and we won't be looking at the Python code super closely, but essentially this is using the Azure Digital Twin API to, I'm scripting my 3D model. And what I'm essentially saying is I'm writing a script that is looking and trying to find data in Azure Digital Twins that may correspond to building 001, right? In my Azure Digital Twin instance that is configured right here, I want to manipulate this part of the Digital Twins graph. So if I start the script, my script is now running. Not much is happening. How is that? Well, there's not much that should be happening because there's no sensor deployed in the house, or more specifically, we haven't modeled the description. But right now, I'm adding a relationship to say that the kitchen contains sensors and contains, as part of the sensors it contains the nose. And now if I go back to Blender, did you see that? Now we do have a visual cue, and I could make that way more visual. I could complement it with sending SMSs to the nurse, etc., etc. I think you get the idea. But this is real time. Like if I go back into the can of coffee, we will soon get the feedback that we have. That the patient has brewed coffee today. Let's see. I should take a couple more seconds because now the device is smelling coffee. Ambient is evolving. I mean, you see the idea. And I'll just use one more minute on this particular demo. Yes, it smells coffee, but it's more, right? It's also, it doesn't have to be only the artificial nose. It doesn't have to be only TinyML. You could have maybe other devices like a temperature sensor. And this one might be coming from AWS IoT for like care. And this one might be in the living room. So again, like I'm establishing the relationship. And you should assume that this is like whatever I'm doing here manually, like faking the fact that I have a temperature sensor that tells me it's 20.5 Celsius. This is something that would be happening in real time and coming from another third-party system or another IoT platform. If I go back here, oh, interesting. The living room is now like I'm also having a visual cue there. So that's fun. And I think that's more than fun, right? I think and I hope you get the idea. If you don't, but I think the emojis kind of give me some feedback there in the chat. But yes, that's what digital twin is all about. And that's the demo I had. Wrapping things up quickly. There was this question from Visteli Labs. So I don't know if Visteli is actually the name of a person or the name of a company, but updating the AI model. Just a quick side note: it's tricky to do on the Wii terminal specifically, especially erasing the external flash while you're already running code off of it. So it might be a bit tricky. So this is those kind of scenarios where it might make sense to have either to replace the Wii terminal altogether by a slightly beefier device, maybe with an actual operating system, and or use something like Azure IoT Edge as a gateway that knows more about device management and things like that to handle some of the complexity. But that's I'm glad that I had this slide ready for you guys. Wrapping things up, I have a few links coming up, but in a nutshell, my point was really to show you that TinyML is, in my sense at least, it's my definition, it's all about generating meaningful signals, right? And doing so in a very power efficient way and very much off the grid kind of scenarios initially, but then it makes a lot of sense when you start thinking IoT, more specifically Internet of Signals, like I mentioned a few times, Internet of Signals as in, you have tons of signals coming from either real devices. Some of them might be using TinyML, some of them might not, and you have other systems, but all those signals, you want to mash them up together to like build those really complex and rich digital twin scenarios. And you really want to like use TinyML for what it's good at and not hesitate to complement it with the cloud whenever you need that dynamicity, if that's a proper word, and you need that versatility, at least in terms of like really having live systems, which TinyML might not always allow you to do, and or embedded doesn't necessarily allow you to have very dynamic and devices and behaviors. Like I said, a few links to wrap things up. Hopefully, one of the moderators can maybe post them in the chat, because I'm pretty sure I don't have the powers to do that. But the GitHub repo with all the source code for the artificial nose, the bill of materials, check it out. There is an actual dev kit that you can get straight from Seed Studio that will get you all the hardware you need, but you don't need much. It's only a weir terminal and the gas sensor, pretty much, that you need to build the artificial nose. There's a great video that I worked on with my colleagues from Microsoft AI. I highly encourage you to check out aka.ms/AI nose. Some really great pointers, some interactive online demos to try the nose, even if you don't have the nose and don't have the sensors. So if you want to get your head around the concepts, how a model that smells even work in the first place, that's all part of the resources that you can find there. And that's it. So I've been told that I could go slightly over time, which now I did, but I'm glad I did, because I think that the demo, I'm not glad I did. It's not great to go over time, but I think it was important to show you the digital twins demo. And I'll stick around if there's more questions, maybe some that I missed in the chat, but I don't think so. But yeah, questions, comments, I'm around, or feel free to ping me on Twitter, LinkedIn, email, subscribe to my blog, YouTube, you name it. But it's been great fun. Yeah, it's all open source. So hack on it, submit pull requests, improvement requests. I'm always, I'm all ears, pun intended, I guess. Thanks everyone for staying around. And I wasn't even on camera to say goodbye. Now I am.
Benjamin, if you've got the links, we can post them on the chat.
Sure. Yeah. Let me see. I think I have them in my clipboard. So one would be, what did I start with? The GitHub repo.
While Benjamin does that, if anybody has any more questions, we can also take those.
Yeah, I'm definitely planning on sticking around for a few more minutes. So yeah. That's the nose, that's the kit from Seed, and that's what was the last one? Yeah, the aka.ms AI nose. There we go. So yeah, thanks everyone for the kind words. I wish you'd had more questions, but I guess maybe you didn't have questions. No, I mean, my call to action is really for you all to try it out. It's there. It's not much in terms of hardware. You learn a lot, and you learn a lot on whichever it is you're the most interested in. If it's the AI model and improving it so that it smells with even better accuracy, it could be that, or it could be pushing it further in terms of the kind of IoT scenarios that you could light up, a smart fridge that smells rotten food, you name it. But yeah, yep. All right, but I don't think it doesn't look like there's any other questions. So maybe we should go off the air and have a great rest of Imagine everyone. I think there's still a couple of sessions, and have a great weekend too. Bye.